Hey everyone, and welcome back to another Forge College Explainer. I am absolutely thrilled you're here with us today. Think of me as your senior engineer, and we're enthusiastically unrolling a crisp, fresh blueprint right here on the desk. Now, if you were with us for our previous session, Capstone, Build the Infrastructure Guide, you know we really got our hands dirty mapping out physical node architectures and RPC connection strategies. But today we are zooming in on the invisible engine that dictates how all that infrastructure actually gets used. We're diving deep into the economic lifeblood of Web3, why cost models matter, specifically looking at gas versus compute units. So, grab your notebook because understanding this fundamental shift from EVM to SVM cost paradigms is going to completely change how you engineer your decentralized applications. Let's get into it.
All right, let's take a quick look at today's schematic. We're going to start with why networks even charge in the first place. Then we'll introduce what I call the laundromat mental model. From there, we'll split unitization from pricing, put EVM and SVM head-to-head, and wrap up with the real-world developer impact and your next steps. So, let's kick things off with a super foundational question. Why do blockchains actually charge for computation? I know, it sounds almost too basic, right? Especially when you think about traditional web servers. I mean, your users usually aren't paying a direct metered fee every single time they click a button or write something to a database. So why can't these centralized networks just operate for free? Well, the reality is if they did, the entire system would just completely break down. Without a cost model, validators and RPC providers would have absolutely no way to prioritize, limit, or monetize the actual heavy lifting they're doing behind the scenes. To get a bit more precise, there are three really concrete operational reasons for these fees. First up, they limit network abuse. Look, if computation is completely free, there is literally nothing stopping a bad actor, or honestly just a sloppy piece of code, from running an infinite loop and instantly clogging up the entire network. A per-operation cost puts a strict stop to that. Second, fees create a vital market signal. Block space is scarce. During peak demand, a fee market lets validators select transactions that actually pay for their hard work, which naturally prioritizes the traffic. And third, we have to recoup real-world infrastructure costs. We are talking about actual physical hardware buzzing away in data centers: CPUs, RAM, SSD storage, network bandwidth. Fees keep the whole system sustainable without us having to rely on brittle, centralized rate limits.
Okay, to really wrap our heads around this, I want to introduce the laundromat mental model. Imagine two very different laundromats. In the first one, which represents Ethereum's EVM gas, you've got a single timed meter. You just shove a handful of quarters into the machine and it gives you an aggregate allowance of time that slowly counts down. You don't really care how much energy the spin cycle takes versus the wash cycle, it's just one big pool of time. Now, the second laundromat, representing Solana's SVM compute units, uses an itemized ticket system. Here, you have to buy a specific discrete ticket for the wash, a separate one for the high-speed spin, and yet another one for the detergent. It's accounting for very discrete, specific micro-actions.
Now think about how this actually changes your behavior. This analogy brilliantly illustrates how these designs manipulate what developers do. With a meter, you're prioritizing predictability. You just top up your gas limit, fire off the transaction, and assume it's going to cover all the aggregate work. But with itemized tickets, you are forced into micro-optimization mode. If that spin cycle is way too expensive, you're highly incentivized to skip it entirely or batch your laundry differently to avoid that specific line item cost. We can even take this analogy a step further. The EVM laundromat occasionally gives you a refund. Like if you clear out old storage, it's literally like the machine spitting a quarter back out at you. The SVM laundromat, on the other hand, has this strict guard standing right at the door, demanding you state your exact budget before you even step foot inside. And that maps perfectly to Solana's strict pre-flight compute budgeting requirements. So, the absolutely crucial point here is understanding the difference between the structure of the system and the actual cost, and that brings us to unitization. Unitization is the pure structural engineering aspect of the protocol. It's the strict mechanical design that determines how work is actually counted. It asks the protocol level question: does reading from the specific piece of state cost 1 unit, or does it cost 10 units? It is literally the mapping of low-level CPU cycles and disk reads into a raw accounting metric. Pricing, on the other hand, is an entirely different beast. Pricing is all about the market economics. It determines the actual currency cost per unit. So while unitization is hard-coded into the protocol's architecture, pricing fluctuates based on dynamic supply and demand, or fixed schedules like base fee burns. When you mix coarse-grained unitization, like a broad gas meter, pricing has to absorb a whole lot of variance.
But with fine-grained units, like our itemized tickets, pricing signals can target specific expensive operations with incredible pinpoint precision. Let's put these paradigms head to head. Mapping them out reveals some pretty stark differences. Under granularity, you see the EVM uses opcode level costs with a ton of specific weights, while the SVM utilizes per instruction explicit budgets. For price dynamism, the EVM relies really heavily on fee market auctions and EIP 1559 base fee burns, whereas the SVM often caps fees per block, leaning much more into parallel validator economics. Now, take a look at the composition row, because this is huge. EVM debits gas sequentially across an entire execution path, while SVM actively incentivizes small parallelizable transactions. For state management, EVM encourages storage clearing through those refunds we talked about, while SVM demands explicit cleanup and rent models. And finally, the tooling naturally reflects all these realities. EVM has mature, very predictable gas estimators, while SVM tooling focuses heavily on strict compute budget measurements and runtime profiling. So, what does all this complex theory mean for you, practically speaking? Well, it reveals a massive shift in developer mindset. If you're optimizing for the EVM, your goal is usually to reorder your work to reduce the aggregate cost. You might actually cram a bunch of complex logic into a single transaction just to optimize the overall gas allowance and avoid touching heavy opcodes over and over. But SVM optimization literally flips that completely on its head. Because you're dealing with itemized overhead, you want to minimize the per-invocation cost. You are highly incentivized to break your heavy logic down into multiple, lightweight, parallelizable transactions. Doing that dramatically improves your success rates on a network that is fundamentally designed for extreme concurrency. Now look, we have to acknowledge that there is no perfectly flawless system out there. There are only architectural trade-offs. Coarse-grained units, like EVM gas, make client-side estimation beautifully simple, but they can easily hide the true cost of hot instructions, which sometimes creates nasty denial-of-service vulnerabilities. Fine-grained units, like SCM compute units, transparently expose all those micro-costs and keep the network incredibly fast and safe, but they undeniably increase tooling complexity for you, the developer. Your client SDKs absolutely must adapt. You aren't just setting a simple global gas limit anymore, you are orchestrating explicit instruction-level compute budgeting and carefully handling UX fallbacks for when those budgets inevitably get exceeded. All right, action plan time. How do we practically adapt our code to this? If you're a developer migrating your architecture, here is your concrete 3-step blueprint. Step 1, prototype your critical transactions early. Please do not wait until production to figure this out. Step 2, measure your unit consumption using truly representative inputs. Run your hot paths and meticulously observe the instruction-level compute consumption. And Step 3, incorporate those findings directly into your client-side cost estimation and your user experience. The absolute last thing you ever want is to surprise an end user with a failed transaction simply because your pre-flight compute budget was estimated incorrectly.
And that brings us to the end of today's explainer. The big takeaway I want you to have today is that unitization isn't just some abstract protocol detail. It dictates the very shape of the code you write. As you get ready for our next lesson, Mechanics of Gas and Compute Units, I want you to pick one representative transaction from your recent projects to bring along in profile. But before you go, I want to leave you with a question. Is your current dApp architecture fully taking advantage of parallelization, or are hidden compute costs quietly holding your app's performance hostage? To continue your transition journey, dive deeper into these topics and explore the rest of our Web3 curriculum, head over to forge.college right now. I'm your host, and I absolutely cannot wait to see what you build next. Catch you in the next explainer.